Dear students, today we will discuss about the residue classes and the complete residue system. Residue classes and the complete residue system. So what is a residue class? We consider a fixed modulus m greater than 0. Then consider the set of all integers x such that x congruence to a mod m. Consider the set of all integers x such that x congruence to a mod m. So suppose this is denoted by a cap, then this is called the residue class a modulo m. For a fixed modulus m, the set of all integers x which satisfies the condition x congruence to a mod m, which is denoted by a cap, then that set is called a residue class modulo m. So what is actually a cap? A cap consists of all the integers of the form sum a plus mq. Agreed? So x congruence to a mod m means it is a set of all x of all in such integers x such that m divides x minus a, that equals set of all x fall in such that x minus a equals mq or x equals a plus mq, where q equals 0 plus or minus 1 plus or minus 2, etc. So this is the a cap consists of all the integers is of the form x equals a plus mq. A cap consists of all the integers of the form a plus mq, where q equals 0 plus or minus 1 plus or minus 2, etc. Now, by using this definition, we prove a result. There is a theorem. The theorem says that for a given modulus m, a cap equals b cap if and only if a congruence to b mod a. A congruence to b mod a. For a fixed modulus m, a cap equals b cap if and only if a congruence to b mod a. How? Let's imagine why this proof is in this way. What is a cap? According to our definition, a cap is set of all integers x such that x congruence to a mod m for a fixed modulus m. Similarly, b cap. What is b cap? B cap equals set of all x such that x congruence to b mod m. Means this a cap is rewrite as a cap equals some x m divides x minus a. That is a cap equals set of all x such that x equals some a plus m q1, where q1 equals 0, where q1 fall in such. Agree? Similarly, what is b cap? B cap equals set of all x such that x equals some b plus m q2, where q2 also fall in such. Now, a cap equals b cap. A cap equals b cap means, that implies a cap equals b cap means a plus m q1 equals b plus m q2. That means, so what is a minus b? A minus b equals m into q2 minus q1. q2 and q1 are integers, so immediately that means m divides a minus b. q1 minus q2 or q2 minus q1 fall in such. Agreed? So m divides a minus b. M divides a minus b means a congruence to b mod m. What about the reverse inclusion? When a congruence to, for the reverse inclusion, when a congruence to b mod m, that implies m divides a minus b. That means a minus b equals m into some q2 minus q1. So finally a cap equals b cap. So the reverse inclusion is also immediate. Agree? A minus b is this one. So that means a minus mq1 equals b plus mq2. So m plus mq1 means consider the set of all A plus MQ1, set of all B plus MQ2, that is denoted by A cap and B cap, that means A cap equals B cap. So means A cap equals B cap if and only if A complements to B mod M. Agree? Yes. Now we consider another result for a fixed modulus M. For a fixed modulus M, the integers x and y are in same residue classes if and only if x congruents to y mod M. Let x and y are any two integers. Choose x and y in such a way that x and y presents in same residue class. Let A be the residue class mod M for a fixed modulus M. Then let x and y presents in A cap. Then we have to show that x congruents to y mod M. X and y fall in A cap means x and y fall in A cap and x fall in A cap means what is x? X equals sum A plus MQ1. Agreed? Y fall in A cap means y equals sum A plus MQ2. Where Q1 and Q2 means Qi fall in set where I equals 1 and 2. I equals 1 and 2. So, what about x minus y? X minus y equals m into Q1 minus Q2. That means m divides x minus y. M divides x minus y means x congruents to y mod m. Agree? So, for reverse inversion, when x congruents to y mod m, that should implies m divides x minus y. M divides x minus y means x minus y is a multiple of m. It is m into sum q1 minus q2. So clearly sum x equals sum a plus mq1 and y equals a plus mq2. Clearly x and y fall in same residue class. So if any two integers x and y presents in same residue class, then x congruents to y mod m for the fixed modulus m. Agreed? Now we consider the next result is the m residue classes. The m residue classes 1 cap, 2 cap, 3 cap, etc. m cap are disjoint and their union is set of integers. Means 1 cap, 2 cap, etc. union m cap is set of all integers. 1 cap, 2 cap, 3 cap, etc. m cap are the m residue classes are disjoint. How? So we have 0 differs from 1 differs from 2 differs from or 0 cap differs from 1 cap differs from etc. differs from m minus 1 and the modulus of ki minus kj. Modulus of ki minus kj strictly less than some m. Modulus of ki minus kj strictly less than m. Modulus of ki minus kj strictly less than m. So for j equals 0, 1, 2, etc. to m minus 1, etc. to m minus 1. And ki differs from kj. Ki differs from kj. Agreed? Okay. Then we have a result. If A congruents to B mod m, if A congruents to B mod m and 0 less than or equals modulus of B minus A strictly less than m, then A equals B. So this is a non-result. If A congruents to B mod m and 0 less than or equals modulus of B minus A less than m, then A equals B. So by using that argument, we have 0, 1, 2, 0, 1, 2, etc. m minus 1. Then A equals B. When A equals B, A congruents to B mod m. Since Ka differs from Kj, for j equals 0 to m minus 1, then 0, 1, 2, etc. m minus 1 are incongruents to 0 mod m according to this argument. Okay, when A equals B, A congruents to B mod m. When Ka differs from Kj, for j ranges from 0 to m minus 1, then this 0, 1, 2, etc. m minus 1 are incongruents to 0 mod m. These are incongruents to 0 mod m means 0 cap, 1 cap, 2 cap, etc. m minus 1 cap are strictly disjoint. Okay. Why? Because we already proved that if a cap equals b cap if and only if a congruence to b mod. So since due to the incongruence we have 0 cap, 1 cap, etc. m minus 1 cap are mutually disjoint. Agree? But every integer x must belongs to one of these congruent classes, that is x equals some qm or mq plus r, where q equals 0 plus or minus 1, etc. and 0 less than qm plus r. Okay, and 0 less than or equals r less than or equals r strictly less than m. We have x equals qm plus r, where q equals 0 plus or minus 1, etc. where 0 less than or equals r strictly less than m. That means x congruence to r mod m. Agree? That means x congruence to r mod m. X congruence to r mod m means x fall in where? X fall in r cap by the definition. Okay, x fall in r cap. And what is 0 cap? 0 cap equals m cap. By this way. Okay, 0 cap equals m cap. Hence the m residue classes. Therefore the m residue classes 1 cap, 2 cap, 3 cap, etc. m cap are mutually disjoint. 0 cap equals m cap by using this definition. Okay. So the m residue classes 1 cap, 2 cap, etc. m cap are mutually disjoint and their union is set itself. Agree? Okay. So all of these three theorems that are depends upon the definition of this residue classes. So residue class A mod m means set of all integers x which satisfies the condition x congruence to A mod m. Agree? Now we define a definition. We consider definition. A set of m representatives, one from each of the residue classes, 1 cap, 2 cap, etc. m cap is called complete residue system mod m. Complete residue system mod m. A set of m representatives, that is one from each residue classes. There are m elements which is from each residue classes. One is from 1 cap, the other is from 2 cap, and so on. One is from each residue classes, called a complete residue system model. So now we define a theorem. So we consider a theorem. Now we consider a theorem. Assume K and m are relatively primes to each other. If A1 etc. Am, if set of all A1 etc. Am is a complete residue system mod m, then Ka1 complete residue system mod m, then their multiples, that is Ka1, Ka2 etc. Kam is also a complete residue system mod m. If K and M are relatively primes, this holds only when K and M are relatively primes. If A1, A2 etc. Am are Am, set of all A1, A2 etc. Am is a complete residue system mod m, then their multiples, products Ka1, Ka2 etc. Kam is also a complete residue system mod m. How? So for come to the proof. If Kai congruence to Kaj mod m, what happens here? If Kai congruence to Kaj mod m, then that means m divides Kai minus Kaj, m divides Kai minus Kaj, that means m divides K into Ai minus Aj, that should implies m divides ai minus aj. That because m and k are relatively prime, hence m does not divide k. Okay. So m divides ai minus aj means ai congruence to aj mod m. Okay. M divides ai minus aj means ai congruence to aj mod m. Ai, that is, it is impossible. Why? That's a contradiction. Why? Because a1, a2, etc. am are is a complete residue system mod m. So a does not, a is in congruence to aj mod m. Thus ka in congruence to kaj mod m. Therefore, these multiples, these products, ka1, ka2, etc., kam also forms a complete residue system mod m. Agree? That is, any set consists of m integers. Any set, if any set consists of m integers is incongruence to mod m, is a, which forms or is constitutes a complete residue system mod m. If any set consists of m integers which is incongruence to be mod m, then which constitutes a complete residue system mod m. So according to that argument, if the system a1 etc. m integers forms a complete residue system mod m, that means all of these integers a1, a2 etc. am or a is incongruence to aj mod m. Thus ka is incongruence to kaj mod m. Therefore the system ka1, ka2 etc. am constitutes a complete residue system. Agreed? Okay. Now we define a linear congruences. What is a linear congruences? Linear congruence means an integer x, that x is an integer x satisfies a polynomial congruence. Polynomial congruence means f of x congruence to 0 mod m is called f of x congruence to 0 mod m is called the solution of the congruences. F of x congruence to 0 mod m is called called a solution of the congruences. What is f? F be a polynomial with the integer coefficients. F be a polynomial with the integer coefficients. So an integer x which satisfies a polynomial f of x, polynomial congruence f of x congruence to 0 mod m is called a solution of the given congruence. Okay. So we also know that when x congruence to y mod m, we already proved that for any polynomial f with the integer coefficients, f of x congruence to f of y mod m. So this is a non-result. If a and b are a congruence to b mod m, then f of a congruence to f of b mod m. So for any polynomial f with the integer coefficients. So for when x congruence to y mod m, f of x congruence to f of y mod m. So every congruence having one solution, for every congruence having one solution has infinitely many solutions. Okay. Hence, f of x be a, hence the solution belongs to the same residue classes will not be counted as distinct. And when we speak the number of solutions of a congruence, we shall mean the number of incongruent solutions. Therefore, every polynomial congruence modulo m has at most m solutions. Every polynomial congruence modulo m has at most m solutions. Because if the congruence has one solution, then it has infinitely many solutions. But if the solutions belongs to the same congruence class, then same residue class, then it will not be counted as distinct. Therefore, every polynomial congruence modulo m has at most m solutions. Agree? So you consider a polynomial that is 2x congruence to 3 mod form. Consider this polynomial congruence. 2x congruence to 3 mod form. It has no solutions. Why? Because no x satisfies this condition. For x is an integer. We already said that x is an integer which satisfies then a polynomial. F of x congruence to 0 mod m is a polynomial congruence, is called a solution, Then f is an polynomial with integer coefficient. Here x is also integers. So consider this polynomial congruence. 2x congruence to 3 mod of 4. It has no solution. Why? Here, what is x? X takes the values 1, 2, 3 and 4. Here x takes the values 1, 2, 3 and 4. Now listen. Here 4 divides 2x minus 3. 2x congruence to 3 mod of 4 means 4 divides 2x minus 3. This is not possible for any x. Why? Because 2x minus 3 is always odd. 2x minus 3 is always odd. 4 does not divide any odd number. So 2x minus 3 has no solutions. Okay. Yes. So 2x congruence to 2x minus 3 means 2x congruence to 3 mod of 4 has no solutions. Agree. Now, consider another polynomial congruence, that is, consider x square congruence to 1 mod 8. How many solutions are here? X square congruence to 1 mod 8. How many solutions are here? Here, what is x? Here x equals 1, 2, etc. 1, 2, etc. up to 8. When x equals 1, so 1 congruence to 1 mod 8, sure it satisfies, so x equals 1 is the solution. When x equals 2 means 4 square, so 2 square, 4. So 4 minus 1 means 3, 3 does not divide 8, so 2 is not a solution. When x equals 3, so 3 square, 9, 9 minus 1, 8, 8 divides 8, so 3 is a solution. 1 is a solution, 3 is a solution. What is 4? When x equals 4, 16, 16 minus 1 equals 15, does not divide 8, so it is not a solution. X equals 5, 25 minus 1 equals 24, must divide 8, therefore 5 is a solution. X equals 6, 36 minus 1, 35 does not divide 8, so it is not a solution. X equals 7, 49 minus 1, 48, so 48 divides 8, thus 7 is a solution, and 64, 8 square equals 64, minus 1 equals 63, does not divide 8, so it is not a solution. Therefore, the solution of the congruence, polynomial congruence, x square congruence to 1 mod 8 are 1, 3, 5 and 7. Okay.